consolidation theory is it assumes that we have a free layer or fine graceful layer, which is very compressible, and at the top you have a free vanish layer. And at the bottom also, the vanish. So when there's a stress increment and you're building a structure, and apply the delta sigma, which is the total stress increment, then excess core pressure along the depth of the plane layer can be predicted by this equation. Round view over round T is CV times square V. So here Z is start from S. And here CV where C sub V is called coefficient of consolidation. And CV is defined as K over there are some time series domains. For example, AD is a coefficient of compressibility, and that is defined in the material. We don't have to know specifically right now. And CV is a coefficient of consolidation, and there is a function of permeability. This is a coefficient of permeability K, and the initial void ratio, and next to water, medication acceleration, and coefficient of compressibility. So you can expect the coefficient of the consolidation will be large for sand, will be smaller for clay soil, right? As permeability decreases, water, it takes more time for water to escape from the soil, like that's a compression. So obviously the CD, the larger CD means that concentration takes faster, the smaller CD means concentration takes more time. So we're gonna talk about this more. And when there's a boundary condition like that, so you have a two-way range condition. Let's talk about boundary condition. First, initial taking is let's assume that the H naught and it's H4 HDR is defined as H. Sometimes in the textbook it will be denoted as H or X of dr. So H dr means that the length of the longest drainage path. So in the K layer, when you have a drainage layer at the top and bottom, water can escape both top and bottom, right? So all will be H in this case, two-way drainage case. Half of H naught, right? 50% of the H naught. So in this case, 4 we call it double drained layer. For double drain system, H will be H naught over 2. Half of H naught. And some case we may have a single drain condition. to drain layer. And so assume that you have the bedrock, rock formation bottom of the clay. Then rock has very low permeability, so the moving wouldn't be easy for to escape through the rock. So it's gonna be just like concrete block at the bottom of the clay. The water can only escape to the top. So in that case, it is considered a single drain condition. In that case, more than 8. The same here is not, right? So that's the Lewis path. Maybe from bottom to top, that's the Lewis path. Right? Double drain layer, middle to top or middle to bottom, over the Lewis path. So that's the boundary condition. Second is boundary condition is when time is 0. So right after the sigma is applied, core pressure at the clay layer. So the initial core pressure, how much will be the initial core pressure? So we apply delta sigma to the clay layer. The clay is fully saturated. And right after you apply this stress, because the water didn't have much time to escape, so delta sigma will transfer to the excessive core pressure. So you have the initial core pressure of delta sigma. And that's gonna be the same for whole clay layer. So Z FC is from 0 to 2H. The reason that I said the 2H is 8, in this case we are assuming the double drain system. The double drain system from 0 to 2H, here will be 1, 2, 0, 1H. 1H. You will develop the same amount of excess core pressure. And right after that, because water escapes with time, so it's going to decrease with time. The third one is at the top and at the bottom of the clay layer, which is right next to the drainage layer. And the key is larger than 0. It says core pressure. That means after you apply this delta sigma, right after that, maybe like 1 second after that or 1 minute after that, at the top here, interface between the drainage layer and the clay layer, the core pressure will just become 0 because they can escape freely. The water can escape freely on the bottom too. So at the depth of 0, depth of 2H, and the time is greater than 0, so that's the boundary condition to solve it. So using this boundary condition, 1, 2, 3, and this partial differential equation can be solved. Solve it. Solution. So, how many variables do you have in here? CD is constant, excess core pressure, and depth and height, 3 variables. Independent variables are time and space. So you develop the core pressure, for example, at the middle. The core pressure at the middle will decrease with time. Right? And maybe quarter point will also decrease with time. But if the magnitude of the decrement will be different from the middle point. So we need to find out the core pressure distribution temporally and spatially, according to that and time. So if you solve that, the periodic consolidation equation, this function differential equation, then the pore pressure will be a function of depth and time. And time so there's some constant like large m or small m here that will be just constant values, and ui is the initial effective excess flow pressure that is developed by the stress function. And the t is the time factor. Why t? There's a time factor which is a function of cv, and the small t is the time the effective time value that we use. H is that the length of the discriminant path. And Z, the depth factor, is the depth over H. So here what we are doing is that this is, imagine this parameter, so no unit. And the depth factor is also length is divided by the length, so it doesn't have a unit. So this is a analytical and exact solution of that partial differential equation. So you can solve this equation to get the excess pore pressure like 1 month later at the middle of the day later, or 2 months later, 1 year later, after you apply this stress instrument. Either you can use some radical solution for that. So if you solve this, the dome drain system, clay layer will be what? 2H, we have sand over the upper face, the bottom, we have sand. All the excess pore pressure look like. Excess pore pressure at time 0 will be just like flat, right? And this much will be by delta sigma. So the excess pore pressure at the initial will be the same in the magnitude of the stress increment. And as time goes by, at the drainage, at the top and at the bottom, the excess pore pressure being 0. So it will be yes. And as time goes by, like this, and eventually the excess pore pressure will just go to 0 for whole plate. So, 0 and what about single drain system? Single drain system. Let's assume that you have a bedrock. The bottom drain. The sand layer, you're compressing it, then this is the page. It says pore pressure. The initial will be like this flat over the layer depth, and decrease show this curve very accurately. Then, excess pore pressure varies depending on how much that weight is increased, or how much the weight is added on top of the layer, right? So it doesn't give you like very standard value. In general, we want to convert it to the percentage number. Like we want to say consolidation is completely 50%, or consolidation is completely 95%, or it has just started, so it will be like 10% degree of consolidation. So there's a parameter in our taking from here, use degree of consolidation. We use the degree of consolidation to describe the weight of the consolidation or status of the consolidation for the time. This degree of consolidation is sometimes called as consolidation ratio. So that is for this parameter, we use UC, the capital UC. Then we have a clay layer with a two-drain double drain system. And at the middle point or any point, so any point at the depth of C, consolidation ratio is defined as follows. This consolidation ratio. Consolidation ratio can be defined as a function of the void rate change. So this is a graph void ratio versus void rate stress. They say that this plane has this kind of compression curve. Then initial void ratio for the original the stress is V naught, and when the delta sigma is applied, the consolidation ratio can be defined as the void ratio before consolidation minus the current void ratio, or the void ratio at the time in question, over the void ratio, the initial void ratio minus current final void ratio. Consolidation ratio, we have to convert this void ratio into the excess curve ratio, because this is something computed. And then linear, you assume all this linear. Okay. convert the void ratio is a change in void ratio into the effective stress change. So assuming that this part is almost linear. Then look at this part. So when the time in question, the void ratio is B, and at this time, what will be the excess core pressure remaining? Excess core pressure is remained by this constant. Let me give you an example again. So this was the initial point, and you apply the delta sigma. So then the total stress is increased by delta sigma, and the effective stress will have to increase eventually by delta sigma. Because this is pressure goes to zero, then amount will be transferred to the effective stress. So this amount is delta sigma. At the same time, this is the amount. This is the initial effective pressure. So at the time zero, excess pressure is generated by this much, and as time goes by, this will decrease, and eventually the excess pressure will go to zero, and effective stress will become small. So from that concept, we can define this void the conservation ratio in terms of effective stress, and we can change it to the excess pressure stress. So, in the end, the degree of consolidation is defined as a function of the excess core pressure. Here, U is the excess core pressure at the time in question, and UI is the excess core pressure at the initial, at the beginning of the consolidation. So, when the U goes to zero, the excess core pressure goes to zero, degree of consolidation is what? 1, right? 100%. And at the time, the initial excess core pressure, the excess core pressure is the same, the initial excess core pressure is the zero, so when that part, effective is 0%. So this degree of consolidation ranges from 0 to 1 or 0% to 100%. So we can plug we can plug this law equation into this degree of consolidation equation. Then we can simplify or we can express the degree of consolidation in terms of this complicated equation. So So from this equation, we can actually draw the degree of consolidation along the depth and a series of four different time vector. So and that chart is called as isochrone or consolidation ratio chart. In this chart, you have our x-axis, you have degree of consolidation at the x-axis. You see y-axis you have an f vector, capital Z, and capital Z ranges from 0 to 2. Right? In the double J system, the depth will be it will extend to the 2h. In the single J system, it will extend to 1h. And equilibrium consolidation starts from 0 to 1 linearly. It will be symmetric for the and here maybe time factor is like 21, and as time increases, the isochron will look like go close to 0, close to 1. So here maybe time factor is 0.9. So for example, when the time factor is 0.9, at the middle, it's about 8.6. So when time factor is 0.9, 86% of the initial excess flow pressure at F1 so maybe at the core point will have different degree of consolidation. So three core points will have different degree of consolidation. In the middle you have always the slowest and the lowest degree of consolidation. So when the degree of consolidation is 86%, it means, let's say you have 100 kilopascal of the excess flow pressure at the initial. Then 86 kilopascal has to be only 14% and 14 kilopascal is left as the excess flow pressure. About average, if we are U or UABG for a given T for a given time factor, you can find or you can draw this kind of an isochron for that and that factor C. And when the consolidation is completed, so all plate layer has 100% degree of consolidation, then we have a line at the right side, right? And at the initial line we get here, right? So this much area of this hashed area is the represents the how much consolidation is over. So we can integrate if you integrate this equation over the depth 2h, then you get the you eliminate the depth factor z, and only remain the t, the time factor will be in the equation. So the final is like this, where you can see is 1 minus 0 to infinite 2 times exponential and this equation is depends only function of time factor t, right? And regardless of depth of the space. And the average degree of consolidation is less than 60%. You can use this calculation. So, by this area integral, we can derive this equation for the average degree of consolidation. Instead of using this complicated equation, we can simplify it and we can use these two for flexible workers. When the degree of consolidation, average degree of consolidation rate is less than 60%, we can use this equation to estimate the time factor. Or the degree of consolidation 60%, not less than 60% in this equation. It's kind of approximates. Or you can estimate the time to take like that percent of the degree of consolidation. For example, like you want to know 90% of the how much it will take until the 90% of consolidation is complete. Then you can plot the 90% because 90% is 60, so you can put 90%. Then you can get the time factor, and time factor t is what? CV times t over x squared. Right? We know the depth of the clay, and we know the CV of the clay layer that can be obtained using that leverage consolidation test. So then we have this multi. Or you will know that after 6 years, after 10 years, how much consolidation will be completed. Then you can find the t and then manipulate this equation to get the t. The settlement. I'm rushing too fast, but settlement, this equation can be used like 1 year after, how much settlement will occur? 2 years after, 2 years later, how much settlement will occur? Then you will get the time factor for t for 2 years. Then use the time factor to get the degree of consolidation. Then you drop to this equation and you get the S settlement. And this SC coupling factor is primary consolidation. Over primary consolidation settlement is determined by the compression index. And we usually get the strength of the so that will be the ultimate settlement for the primary consolidation. And then they will occur eventually as time goes infinite, but we want to know when you use these two equations, when you don't know like where which equation to use, then use this chart. The first chart, you have to know either ULDG or the time factor. From that, your question is asking for the region less than 60% your conservation or larger than 60%. From that, you will determine, you know which equation to use. Then use